So, welcome to the final London Learning Lead of term. And this week we're very pleased to welcome Heather Macbeth, all the way from New York City, who's going to tell us about Fourier series.
Thank you, Kevin. So I want to run this mostly as a chalk talk, adapted to the virtual realm. And so let me start by stating the theorem I want to prove. So I'm going to let S1 considered as a subset of the complex numbers be the unit circle. And I'm going to equip it with the Haar measure, which we have in Lean thanks to the work of Floris van Doorn. And I'll call that mu. And we choose the convention that this is normalized to have volume 1. And now let me recall what it means to take the L2 space of functions on the circle. So I'm going to define the L2 space to be the set of functions from the circle to the complex numbers, such that the integral of f of z norm squared d mu is finite. So this construction, the L2 space, exists in Lean thanks to the work of Rémy Desgen. A couple of subtleties. So we say that f has to be a measurable function for this integral to make sense. And we're also going to identify functions that are almost everywhere equal with respect to mu. So this is a Hilbert space. So the Hilbert space construction is still thanks to Rémy. So the way in which it's a Hilbert space is that for two functions in L2, if we want to take the inner product of f and g, we say that's the integral over S1 of f complex conjugate times g. And this is well defined. Since if we take this integral we're interested in, this, by Holder's inequality, is less than the square root of the integral over S1 of norm squared f times the integral over S1 of norm squared g. And both of those are assumed to be finite for L2. So next I want to recall a second Hilbert space. The second Hilbert space is little L2, which is defined to be the set of sequences or functions from Z to C, for which the sum, the infinite sum over Z of the norms, or in this case, I guess the absolute, the moduli is less than infinity. So people usually choose their little L2 to be indexed by the natural numbers, but in this case, it's going to be easier to consider the integers of the indexing set. And since there's a bijection between them, it doesn't really matter which. And this is also a Hilbert space. we have that the inner product between two functions is going to be the sum over z of complex conjugate of f times g. And again, this is well defined by the appropriate version of Holder's inequality, in this case for infinite sums. So the theorem I'm going to talk about proving is that there exists an isometric isomorphism from L2 of the circle to little L2, called hat in notation. And so it's going to have the property that for all f in L2 of the circle and all integers n, f hat of n, so that is take this isometric isomorphism to get an element of little L2 and then take the nth component of the sequence, is the integral over the circle of z to the minus n f of z du. And let me remark on a couple of consequences of this construction of an isometric isomorphism. So, firstly, this is called the Fourier series, considered as a function from z to c. So people usually consider the Fourier series as a map from functions on the interval to sequences, but you know, given that I mean, it's really functions on the interval, you know, with an identification with functions on the real line that are periodic. I mean, there's no reason not just to consider them straight up as functions on the circle, which is what I'm doing. And people also often, you know, initially consider a version of Fourier series which is real-based, in which you're taking the inner product with trigonometric functions, and then later switch to a closer analog of what I'm doing, where you take complex functions and take the inner product with e to the power of I and z. But when you switch to consideration of the circle rather than the interval, even the e to the power of I and z disappears, and you really are just taking the inner product with polynomial functions themselves on the circle. And then the second point I want to make is that by setting it up in this way, by construction as an isometric isomorphism, it automatically follows that for any function f, the norm of f is equal to the norm of its Fourier series, or if I want to take the squares, I can just write out what that means in terms of the definition of the norms. That is that the integral over the circle of f of z squared d mu is equal to the sum over the integers of f hat of n modulus squared. So this is Parseval's identity. And this just drops out for free. And to my knowledge, this is somehow the only new part to formalization. There have been formalizations of Fourier series, first in whole light about 10 years ago, and more recently also in Isabelle and in MetaMath. But by setting them up in a somehow more elementary way without necessarily mentioning Hilbert spaces, other parts may become more easily, but I don't think that Parseval's identity has been proved before. Whereas, as you can see, by setting it up in this Hilbert space theoretic way, the Parseval's identity part comes almost without effort. So let me sketch the proof. There are going to be 3 parts. So the first part is that the functions z to the n, considered as functions on the circle, form an orthonormal set in the Hilbert space. This part is quite easy. The second part is that this orthonormal set is complete. Where complete here means that it has dense span. And then the third part is some sort of abstract theory of Hilbert bases. So I want to spend some time outlining in turn how each of these is set up and proved both mathematically and then in Leave. Any questions before I go into the proofs?
Sorry, Heather. So if this is the first time that Parseval was proved, has anyone done Poisson summation in the other systems?
Not to my knowledge.
Okay, very good. Thanks.
1 and 2 are theorems, and then 3 is, what does 3 mean?
Perhaps 3, if I want to state the theorem that will come out, it's the theorem that if you have an orthonormal dense set, then it induces an isometry, an isometric isomorphism.
Thanks.
But I guess this part is really just a part about, a part about Hilbert spaces in the abstract. So let's start with the easy part, so the orthonormality. So this is just a relatively easy direct calculation. If I want to take the inner product of these 2 functions, so if I have en and en, 2 functions of this form, this is the integral over S1 of en complex conjugate times en. So what are these? This is en is z to the n, en complex conjugate is z to the minus n. So this is just the integral over S1 of z to the power of n minus n. And at this point, I just need to prove a little lemma that the integral over S1 of z to the k is going to be 1 if k is 0 and 0 otherwise. And this is fun and easy to prove. So if k is 0, then the integral over S1 of z to the k is just the integral over S1 of 1. And we chose our Haar measure to have measure 1. So that's just 1. And if not, then let me select a complex root of unity, zeta, which is going to be e to the power of pi I over k. So this means that zeta to the power of k is minus 1. And then I can have a measure preserving map sending z to zeta z. just a rotation. From S1 to S1. And since this is clearly measure preserving, we have that the integral over S1 of z to the power of k d mu z is the integral over S1 of zeta z to the power of k d mu of z. And this is just the integral over S1 of zeta to the power of k z to the power of k. And by construction, that's a factor of -1. And so we've got a number whose negation is itself, and that means that that number is 0. Which is what we wanted. And I'll mention that this argument is one more advantage of using the circle point of view rather than the unit interval point of view, particularly if you're phrasing the result in terms of trig functions. There's actually, some work you can imagine in taking the inner product of sine of m theta times sine of n theta, or even worse, because there's 4 cases, sine of m theta times cosine of n theta, and so on, and getting that all of these are orthonormal by means of, iterated trig integration formulas. So
is this something you teach to students, Heather?
What was that?
Is this something you teach to students? I think I've never seen that proof. I mean, I've taught Fourier series, and even in the complex case. I mean, of course, it's also very much related to the fact that you introduce the measure as the Haar measure, because you're really using the invariant and the rotation in this proof.
Yeah, I don't know that I've seen it written down. Of course, it's not very difficult, but I think it works out quite nicely.
Yeah, it's very nice.
So let me, this is-
Sorry, Heather, can I ask another question?
Oh, please, yes.
But in lean, does this look pretty much like what you're giving the human proof?
Yes, exactly. I was just about to switch to lean and show it there. So I know this is supposed to be nominally a talk about lean as well as a talk about math, and I guess I can't stick to the whiteboard the entire time. So let me switch now briefly to lean and just show what this looks like, and I'll do the same thing at the end of sort of every section.
Thanks.
Yay.
Does it work?
Yeah.
Yes, so here we have a lemma saying that if we are taking pi over n, X map circle is the map identifying a real number with the corresponding point in the circle. It's a map from the real line to the circle. So if I take the function e to the power of pi over n times z, then this is the negation of z to the n. And then from there we get that that the Fourier series, the elements of the Fourier basis with respect to L2 are orthonormal. So we consider 2 cases. So given I and j, so we write this in terms of an integral, and there are going to be 2 cases. So the first case, I guess, is when they're the same, and the second case is when they're different. The first case is just, that it all simplifies to 1. And in the second case, we establish that I plus j is non-zero, and then we invoke the fact that This is just some random fact that I proved in the measure theory library. If some left translate of a function negates it, then the integral of the function with respect to a left invariant measure is 0. Filippo, yes?
Filippo, you have your hand up. And you're muted.
Sorry, I didn't know I had my hand on. I didn't mean to. So this.
I think, don't worry.
Okay, I got it. I'm sorry. Well, I take the opportunity to say that your proof before was wonderful. So.
I can't believe you're baking in characteristic not to so early in the theory.
Yes, you're right. That is an unfortunate feature. So yeah, as you can see, this is really, I don't know, I mean, I guess I'm cheating a little bit because I proved this lemma in the context of, left invariant functions on topological groups. But apart from that, it's, 20 lines. Okay, so part 2 is the completeness. Okay, so I'm going to introduce now a second function space. So this is CS1C, so this was introduced effectively by Sébastien a few years ago in the course of the Gromov-Hausdorff project. It's the set of functions from S1 to C such that F is continuous. This is naturally a Banach space. With the norm of F is the maximum of the absolute value, and this maximum exists since the circle is compact and we're considering continuous functions. And of course, there's various work going on here, for example, to prove the completeness and so on, which I won't discuss. So we're going to break the completeness of my orthonormal set into 2 steps. The first step is that the span of these monomial functions En is dense in the continuous functions. And secondly, that the continuous functions are dense in the L2 functions. Okay, so these are 2 quite different arguments, both quite non-trivial. So for the first one, so I want to recall the Stone-Weierstrass theorem. So if I let A be a subalgebra of the continuous functions, which is closed under complex conjugation, and separates points. I'll explain that in a second. Then that subalgebra is dense in the space of continuous functions. So separates points means that for any two function, any 2 points, sorry, Z1 and Z2 in the circle, there exists an element of the subalgebra on which they're different. Okay, so how do we prove this? So the only part of this that I did myself is that I deduced it from the real version. So the real version is even simpler. It's that if we have subalgebra of real functions on S1, continuous real functions on S1, which separates points, then A is dense. And this real version was proved by Scott Morrison. So there are maybe 2 steps to that real version. Both of them are quite time consuming. It was a big project. So the first step there is that for all F in that subalgebra, in fact, the absolute value of F is also in the subalgebra. And the proof here is that we apply the classical Weierstrass theorem so that's the classical theorem on approximating functions on the unit interval by polynomials. Better actually if I said not the unit interval, but the interval -1 to 1, because I'm going to apply that to the absolute value function. So what we get is we get a sequence of polynomials approximating the absolute value function. So I apply each of those polynomials pointwise to my continuous function, and I get more things, which, because it's a subalgebra, are also in the subalgebra. And this gives me, oh, sorry, I should have said in the topological closure of A, sorry. So, so I have a sequence of functions which have to be also in the subalgebra. And then their limit is going to be the absolute value of F, and that therefore is in the topological closure. So this means that the topological closure is a sublattice of CS1. And then step 2 is that any non-empty sublattice of CS1 which separates points is dense. Okay, so maybe I'll show the code for this as well. Again, let me emphasize that almost all of this was written by Scott and not by me.
So sorry, what do you mean sublattice here?
So really, you take the pointwise max of 2 functions, or the pointwise min of 2 functions.
Okay.
Those are the meet and join operations.
Okay.
So here's Scott's proof of the Weierstrass approximation theorem. This is for approximating functions on AB by polynomials. And this is a detailed calculation using the Bernstein polynomials. So we have these Bernstein approximations and a theorem saying that they give a uniform approximation to any function on that interval. And then this is manipulated into a theorem on the topological closure. And then finally, we have the Stern-Weierstrass theorem, where we first get the fact that the maximum, the absolute value function is in the topological closure, followed by the deduction that the pointwise max, for example, and the pointwise min are in the topological closure as well, which makes it into a lattice. And now we have the lemma saying that if we have a lattice which is non-empty and separates points, then its closure is dense.
Oh, is that the correct statement of Stern-Weierstrass? That was never what I was told.
Well, and then we deduce, so like I said, then we deduce the sort of the version that I think we're more familiar with, saying that a subalgebra which separates points is dense. But this is just manipulating the two previous theorems. We let L be the topological closure, and then we apply the lattice version. And then finally, there's the part where we deduce the complex version from the real version. So this version, we now have a complex subalgebra of the complex continuous functions, which separates points and moreover is conjugation invariant. And first we prove that so the real subalgebra of its purely real valued elements separates points. So then I prove after that the Stern-Weierstrass theorem, and I get that by applying the real version to that real subalgebra, and then expressing any function as the sum of its real and complex parts and applying the theorem I just proved to that. Questions? I think maybe the only takeaway from the Lean code is that it can be stated very cleanly, like nothing here requires compromises to go into Lean.
I was going to ask what the hypotheses on X were, but I can see them in the tactic state, so it's compact.
Yes, well, I should probably click into this tactic state, but yes, it's a compact space.
So you don't need Hausdorff. Oh, yeah, maybe. Okay. Separates points implies Hausdorff, do you think?
Okay. So now the second part of the approximation step, the second part of the completeness step, I guess, rather, is going to be oh, I guess I'm not quite finished yet because I still need to prove. So that was the end of the proof of the Stern-Weierstrass theorem, but I still need to establish that the span of these monomials is a subalgebra of the continuous functions, which is closed under conjugation and separates points. So it's clearly additive closed. And that to deal with the multiplicatively closed, if I have the product of En and En, that's equal to E m plus n. So z to the m times z to the n is z to the m plus n, so it's closed under multiplication. I have that if I take the complex conjugate of the function z to the m, I get z to the minus n. So it's closed under conjugation. And then to show that it separates points, if I have two numbers z1, z2 in the circle, not equal, we can just apply the function e1, that's the function z itself, and e1 of z, z1 is z1, which is not equal to z2, which is e1 of z2. So even the function e1 on its own separates points. So let me maybe jump back to the Fourier file and show that. I mean, again, as you can see, this is the kind of argument that takes about 5 lines. Great, so here we are showing that we have a subalgebra which is conjugation invariant. So I'm going to, I guess, show here that minus n is in it, and that it's closed under addition and multiplication, which again are just exactly what you would expect. And then we just apply the Stern-Weierstrass theorem to it to get that the topological closure of the Fourier subalgebra is the whole of the space as a C S1 to C. Okay, so next on to part 2 of the completeness step, where I'm going to show that that the continuous functions are dense in the L2 functions. And I might as well switch now to just a compact topological space. With the Borel measure mu. So for any function which is continuous on our space X, we have for all X, absolute value of F is less than or equal to the norm. And that means that if I want to take the integral over the space of the norm squared, this is less than or equal to the integral over the space of the norm of F in the continuous function sense. And so this is just norm F times the volume. And this shows that at least it is strictly contained. Maybe I don't yet know strictly contained, but it is contained in the space of L2 functions. And this embedding is a bounded embedding. So for any F, we have that the L2 norm is less than or equal to the continuous function norm times the square root of the volume. And incidentally, I'm restricting here to L2, but the same considerations work for any LP throughout this section for P less than infinity. So I now want to show the denseness if X is a compact, normal, topological space, and mu is a regular measure, then the continuous functions are dense in L2. So it suffices to show that for any Borel set, S, a subset of X, the characteristic function let's call that chi sub S, can be L2 approximated by continuous functions. So the way I'm going to prove this is, here's my set S. Let me first find a close, closed or indeed compact approximation inside. I'll call that A. And let me also find a good open approximation outside. I'll call that B. And these two approximations together are going to be good enough that if I take the space between them, so this space here in between the two of them, that it can be as small as I want. So this is a consequence of the regularity of the measure. Let me state that.
Do we know that Haar measure is Borel and regular, all these things?
We do, yes. Okay. I think this was all part of Floris's project on Haar measure.
That's a relief.
So since mu is regular, for all epsilon, there exists a compact set A contained in S and an open set containing S such that the measure of their difference is less than epsilon. And now, since X is normal, and A and B complement are closed by Urysohn's lemma, which was proved by Urysohn-Kudryashov, there exists a continuous function, I'll call it f sub epsilon, from X to the unit interval, which is 0 on B complement and 1 on A. And now we can just do the obvious calculation of the difference in norm. So f minus f sub epsilon squared in the L2 norm is equal to the integral over X of the absolute value of f of X minus f sub epsilon of X. So this is going to be 0 on both B complement and on A because the characteristic function, maybe I should have said that this f here is the characteristic function of S. So they agree on B, they agree on B complement, they agree on A, and in the middle they can in any case be less than 1, so this is less than or equal to the integral over just that little tiny middle part of something that is less than or equal to 1. So this is less than or equal to the measure of the middle part, which is epsilon. Okay, let me now show this in Lean. I have to say this was really quite unpleasant to prove, just because it's not so nice to work with the extended non-negative reals. In Lean, you have a lot of automation that is available for the real numbers, which is missing in this more general context. So,
so you mean here the measure is valued in extended non-negative real numbers?
Yeah, so the measure of a set is an extended non-negative real in them. So here is the proof, and it really is quite long and quite painful. So we are going to prove that if we have a weakly regular measure mu, sorry, and Lean has given me a horrible orange bar as it tries to load this proof. If we have a weakly regular measure mu, then the space of bounded continuous functions has topological closure, which is the whole space. Yeah, so we've got the normal assumption, the Borel assumption. This is actually stated for functions into Banach spaces. So the reduction to the characteristic function is just some random about simple functions, which required a refactor of the characteristic function, the setup for defining the integral by means of characteristic functions. But then we switch to approximating that characteristic function. We find some eta, and we're going to require that the C in question plus itself to the power of 1 over p or whatever is less than epsilon, which itself is a pane. And then we extract the appropriate set using regularity of the measure, and we apply Urieson's lemma to get our approximation function g. And then there's just horrible, stupid, explicit calculations for the rest of the proof, but it works out fine. Okay, and now we are left with what I was calling step 3 before, which is just our abstract theory of Hilbert spaces.
Heather, can I ask? So it seems like analysis is hard in Lean, like something where you have to, where it's not just equal signs the whole way through, but breaking things up, and like that last part. Is that the part that's the hardest of this proof, where you actually have to estimate something?
At least it's the hardest part of this project that I did myself. I mean, throughout this project, I was invoking all sorts of difficult theorems proved by other people, but that is the most difficult part that I myself contributed.
And is there any hope of some kind of tactics that could make that
one thing that it would be really nice to have would be a tactic that helped prove inequalities the way that humans prove inequalities. The way that humans prove inequalities is they write down on paper, blah less than or equal to blah, less than or equal to blah, less than or equal to blah, less than or equal to blah. And humans are actually quite smart about the way that they set up a proof like that. They arrange it so that each step, in fact, typically what they would do is they would have intermediate equal steps. And for an inequality step, they have precisely arranged it so that the two expressions, one of which is less than or equal to the other, have precisely one difference. And, so maybe, you'd have each of the
calc blocks can do.
So indeed, you want to be able to do this using a calc block, but you want, I think, a tactic that applies all of the obvious lemmas according to the way the person set it up and gives them the goals that are needed. Like, for example, say that your goal is, say that the human has set up that the current goal is a to the power of p plus sine of b times c plus d less than or equal to a2 to the power of p plus sine of b2 times c plus d. You want a tactic that tries to prove this by applying the theorem on when a number is less than or equal to another number. So that will sort of apply the additive inequality lemma to get rid of the d's. And then there will be another one which, gives you a goal of proving that c is non-negative and then strips away this. And then gives you another goal of, proving that the b1 and b2 are in the interval on which sine is monotone and strips away this. And then finally gives you a goal of proving that the a1 and b1, the a1 and a2 are non-negative and strips away that. So somehow that eagerly applies inequality lemmas and leaves you with the sort of checking that are non-negative or in the appropriate interval arguments. So I think it would be very useful to have a sort of greedy monotonicity tactic like this, because that's actually how humans write inequalities. And then they just sort of implicitly in their head check the sign, the sort of side conditions. And then, when we write an inequality proof, we alternate steps like that with equality steps where you sort of do your rearrangement in order to put you in position for the next big inequality step. So that's how humans prove inequalities. And I think it would be really nice to have better tactic support for that.
That'd be great, yeah, thanks.
For the record, there is already a monotonicity tactic that Simon Hudon wrote already several years ago, but it's not quite at that level.
I think it could be extended to do this kind of thing. And I mean, once I know more about tactics, I'd love to work on that a little bit.
And it's also very much related to Rob Lewis' PhD thesis. But, the issue with Rob's thesis was the transition from Lean 2 to Lean 3 happened in the middle, and somehow his work was a bit lost in this transition. And it was probably too slow anyway to be realistic in Lean 3, but he certainly intends to return to this at some point. And there is another part, so there is what you've said, but also the fact that linearis is not working for extended non-negative real numbers is really a pain indeed. And it was also very painful in the first part of the liquid tensor experiment project. I don't know, I guess there is no obstruction. There should be another algorithm. Maybe Fourier-Motzkin elimination is not good enough for this, but something else should be good enough. And I'm very, very optimistic that this issue will be solved, because otherwise it's completely blocking analysis.
I don't know. I mean, so I don't know about Rob's thesis apart from the work on linearis, and this is almost orthogonal to linearis in that it's sort of, I want something that isn't, completely perfect over the reals when there are sort of no side conditions to check the way that Rob's linearith is. I want something that is imperfect but greedy and sort of does all of the stuff except for checking the side conditions, which then you can check yourself. Because I think that sort of the way that humans traditionally set up proofs without realizing it is actually designed to be easily checkable for this particular, imaginary tactic that I'm describing. Anyway, let me, if you don't mind, in my last 3 minutes, quickly describe step 3 of the proof, and then we can return to this in the discussion. So just quickly to say step 3, so what we want now is so some stuff on Hilbert bases. So what do I want here? So if I let E be a Hilbert space, so the way that you would present this in traditional math is that you'd say, we define an iota indexed Hilbert basis for E to be a collection, maybe I'll call this E sub I for I in iota, which is orthonormal and has dense span. And then you just state it as a theorem that a Hilbert basis of E induces an isometric isomorphism from E to little L2 modeled on iota. But in Lean, I adapted a beautiful idea of Anna Bonin and set it up in some sense backwards. So I adapted this idea from the way that it's done in the sort of, you know, abstract linear algebra basis library to results in Hilbert spaces about Hilbert bases, and but it's you know, very much a close analogy. So we're going to define now an iota indexed Hilbert basis of E to be an isometric isomorphism from E to little L2. And we say that there is, given such a thing, an associated family. So let's say the basis is called B. There is an associated family B sub I for I in iota of elements of E. So we call this in Lean sense a has co-E to fun, so a coercion from the basis B to functions from iota to E, sending I to the isometric image under this isomorphism of somehow the characteristic function supported at I. So it's 1 if j is I and 0 if j is not equal to I in L2. So with now the thing that you actually really want to use in almost all applications, the isometric isomorphism as being your definition of Hilbert basis, we now make it a theorem that given an orthonormal basis, so given an orthonormal complete set, BI, we have a construction of a Hilbert basis whose coercion to a function is that set. So as I said, the advantage of this point of view, which sort of turns the usual approach on its head, is that in almost all cases, what you really want to use is the isometric isomorphism, and having this available as your package makes your life a lot easier. And then the sort of implementation detail of constructing a Hilbert basis is reduced to a sort of constructor for Hilbert bases. So let me maybe just explain the proof of this theorem. We just have that given an orthonormal set, Bi in E, clearly the map from L2 into E, given by sending F to some I, Fi, Vi, sorry, Bi, is an isometry onto its image. And since L2 is complete, that means that the isometric image is complete. A complete subspace of a Hilbert space is closed, but since it's also dense, this means that it's a surjective map. And I'd say the hardest part of this is just the completeness of little L2, which is a classic result, which I really enjoyed proving. So now we can jump back to, so we instantly have the construction of a Hilbert basis by our previous two results that Fourier series are orthonormal and dense. And let me just explain how then all of the results that we wanted about Fourier series become reduced to facts about Hilbert bases. So we can make our Hilbert basis in a couple of lines by invoking the constructor for Hilbert bases in terms of the orthonormality and completeness. And now by construction, the ith element is going to be the integral over the circle against t to the minus I or z to the minus I. So this is the ith Fourier coefficient. It also follows automatically that the sum of the Fourier coefficients times the functions e sub I, L2 approximates the original function. And Parsifal's identity follows almost instantly just by comparing the appropriate norms. Okay, thank you.
Thank you very much.